Alrighty, folks. So today we're talking about section 4.4, which is called the shape of a graph. And it introduces a couple more definitions and ways to find things. So we have a graph it's not a graph, it's a function. I got lured in by the title name. A function is concave up on an interval if, so function f of x, if f prime of x is increasing, right? And I mentioned last time that this is going to relate to last section and talk about the second derivative. And so we know last time we learned that a function was increasing if its derivative was positive. So how do we know if the first derivative is increasing? Well, that happens if the second derivative is positive, right? And then we also have a function f of x is concave down on an interval if the derivative is decreasing on that interval, which, of course, as we learned happens last time, a function is decreasing if its derivative is negative. So f prime is decreasing if f double prime is negative. Right? So now, in addition to figuring out increasing and decreasing, we can figure out concave up and concave down by looking at the second derivative. We have a sort of analog to critical point. It's not quite the same thing, but if f double prime of c equals 0 or f double prime of c does not exist, right? So it sounds an awful lot like critical point so far, and f double prime of x changes sign at c, then c is an inflection point, right? So in other words, if we do so all the things that we do to check if a point is a local extrema, if we do all of them but replace the first derivative with the second derivative, we haven't found extrema anymore, we found inflection points. Right? So we figure out where it's 0 doesn't exist, then figure out whether it changes sign. The last thing we have new in this section is the second derivative test. And that says if c is a critical point, and the second derivative of c exists, if the second derivative of c is positive, then c f of c is a minimum. If the second derivative of c is negative, then we get a maximum at c. But this is a tricky one. If the second derivative is equal to 0, then we know nothing. Like unto Jon Snow, we are ignorant of anything that might be true about this situation, right? It might be a maximum, it might be a minimum, it might be neither, right? So while the second derivative test might be a little bit easier to pull off, we have to take the second derivative twice or take the derivative twice and then plug something in, as opposing to taking the derivative once and plugging two things in. right? So which one's easier depends on a lot of factors. But if the first derivative test, if it doesn't change, then it's not a critical point. In the second derivative test, if it's equal to 0, then we don't know what's up, right? It might be maximum, might be a minimum, might be nothing. We're unsure. And that at that point, we have to try other tests. So, with all this stuff under our belt, let's do some problems. So let's find the concavity and inflection points for f of x equal x to the 7/5 minus x to the 3/5 plus x. All right. So if we're going to find concavity and inflection points, we have to get all the way to the second derivative of f. So to get to the second derivative, we have to get to the first first. These are thankfully just power functions. So we bring the powers out front, and we subtract 1 from the power. We bring the power out front, and we subtract 1 from the power. And this is linear, so we just get its coefficient. All right. So that was our first derivative. Our second derivative is going to be more of the same. We're going to bring the power out front and multiply it and subtract 1 from the power. We're going to bring the power out front and multiply it and subtract 1 from the power. And the derivative of a constant is just 0, so we're done at this point. All right. So now we need to know where it does not exist. Right? And if we look at this, we can see that there's secretly some fractions hiding in here. Right? Anytime you have x to a negative power, this does not exist at x equals 0. Right? So that's one of our potential inflection points. And then, we need to figure out where f double prime of x is equal to 0. All right, so this is 14/25 x to the negative 3/5 plus 6 to the 25 x to the negative 7/5. So I did this one partially because it's quite likely that you won't remember how to factor things like this. Right, remember when we have fractional or negative powers, really the only hope we have is pulling out a common factor. At least that's our first hope. Right, and we always want to, if all of our terms have x in them, we want to pull out x. And maybe I'm going to pull out x over 25 just to get rid of those awful fractions. And we want to pull out x with the lowest power, right? So negative 7/5 is smaller than negative 3/5. So we pull that guy out. So we're left with just 6 from that term. And here, I know I'm still going to have that 14. We pulled the 25 out. I'm still going to have an x because there were more x's than we pulled out to start with. And I want something so that if I add the power here to the power that we pulled out, we get the power we started with. So I know that has to be 4/5. Because if I'm going to get negative 3/5 out of negative 7/5 by adding, I need to add 4/5 to that. Right? So this comes down to 14x to the 4/5 needs to equal negative 6. And right there I can stop because I know there's not going to be any solution. Right? Because remember, the numerator of a fractional power behaves more like the exponents that you're used to as opposed to roots. Right? This is secretly 14 times the 5th root of x to the fourth, right? And x to the fourth can never be negative, right? The fifth root of x can only be negative, or the fifth root can only be negative if what's inside it is negative. And x to the fourth can never be negative. So there's no solution to this equation, right? So our only potential inflection point is at x equals 0. So like I said, this is just copying what we did last time, but with the second derivative. So we're going to draw our number line. We're going to write down all of our potential inflection points in this case, not extrema, but inflection points. And then we're going to pick a number from below, above and below. So I'm going to pick -1 as my number below 0, right? And here, I'm going to do a tricky thing of noticing that, well, -1's a really nice number, for one thing, right? But I can notice that x, let me see how to phrase this. -1 to the -3/5 is still negative, right? Anything negative to the -3/5 is still negative because we have an odd power up here, right? Same to the -7/5. Because that's an odd power, I know that that's going to be negative, right? So I'm subtracting two negative numbers, and I know that this guy is going to be negative. All right, same thing for the second derivative here. I'm going to choose 1 because it's a nice, easy number, right? And so I know that's just going to be 14/25 plus 6/25, right? We're just going to get positive numbers out of that. We're adding two things together that are positive, so we get positive and negative, right? So if we remember from above, we are concave up when the second derivative is positive. So that's from 0 to infinity. We're concave down when the second derivative is negative. So that's -infinity to 0. And 0 is an inflection point, right? Because we changed from negative to positive, right? One difference in this section for finding inflection points instead of classifying extrema is that inflection points don't care whether it's changing from negative to positive or positive to negative. It just cares that it's changing, right? So we're changing from negative to positive, and that counts as changing, so 0 is an inflection point. So let's see. Right. So let's do another problem. Same for f of x equals x to the fourth minus 3x squared. Right, so we take the first derivative, we get 4x minus, 4x cubed minus 6x. Using our rules for power functions, we take the second derivative, we get 12x squared minus 6. All right, which maybe we want to go ahead and rewrite as 2x squared minus 1. So, we need to check for does not exist. It exists everywhere. There's nowhere it doesn't exist. So we have to go to this equaling 0. All right, we can divide both sides by 6 and add 1 to both sides. We can divide both sides by 2. And we get that x equals plus or minus the square root of 1/2, or 1 over the square root of 2, whichever way you want to write it. All right? So, those are our potential inflection points. That's what we put on our number line. So we've got -1 over the square root of 2. We've got +1 over the square root of 2. And we just have to pick numbers in between them. So I'm going to pick, let's say, -1 over here. So f double prime of -1. This guy is simple enough, I don't mind just plugging it in. Right, that's definitely positive. Looking good there. 0 is a good number. It's always a good plan if you can plug in 0. It's always going to be the simplest thing. So that's always just going to give the constant term. So that's negative. And up here, I can plug in +1. Right, and so I notice that this is also going to give me 6. So we get a positive number up here. Right, so we're concave up from wherever it's positive, so from -infinity to -1 over root 2, and then from 1 over root 2 to positive infinity. Right, it's concave down wherever it's negative, so that's going to be between the 2 points. And in both of these cases, it switched, right? In one case, it switched from positive to negative, and the other from negative to positive, but we don't care about this distinction for inflection points, so both plus and minus 1 over the square root of root 2 are inflection points. Right? So we're going to take a somewhat odd detour to talk about limits for a second. L'Hopital's rule, if anybody's heard of that before. So we're going to take a brief detour to talk about that. Then we're going to come back to this sort of thing and figure out how to take all the stuff we learned about the shape of a graph to help us make some quick sketches of graphs. But next time, L'Hopital's rule, then we'll talk about graph sketching. It's a weird order, but that's the way they do it. I'll see y'all then.